Today we are going to be continuing exponential functions. So we have our equation, our first equation, f of x equals 2 to the power of x. So we're going to use that equation to fill in our table values. I'm going to start with the exponent of 1. 2 to the power of 1, we know, is 2. And then 2 squared, 2 to the power of 2. 2 squared is 4. And then 2 to the power of 3 is the same thing as like saying 2 times 2 times 2, which would be 8. All right, what about 2 to the power of 0? So often it's thought, okay, there's a 0, there's probably going to be 0. You could put that in your calculator to see, but it's actually going to follow this pattern. If we're going times 2 times 2, to go backwards, instead of times 2, it's divided by 2. So 2 to the power of 0, or really anything to the power of the 0 that I know of other than 0, is 1. And we're going to learn more about powers of x, like exponent rules, power rules next week. But if we raise it to the power of -1, that's like dividing it by 2 again, going backwards. So it's going to be 1/2. So we'll learn that next week. But until then, you're welcome to put this in your calculator to check. But it's following that pattern. So let's graph these points. We have when x is -1, y is 1/2. Then 0, 1, 1, 2, 2, 4, 3, 8. Connect those points. And it's asking for the shape of the graph. And when it's asking about the shape, in this case, it's meaning growth or decay. So what's this one going to be? Growth. We can see it's increasing from left to right. It's a positive. It's increasing. It's a positive relationship. So the shape, I would say exponential growth. All right, and where does it cross the y-axis? Right, so we can see it in the table right there. We can see it on the graph right here. It crosses at the point 0, 1. And that's our a value. Our a value is 1. Now remember in our equation for exponential functions are a times b to the power of x. But if you look at the function here, it only has one value. It only has the 2, which in this case represents the b. That's our b, our base value. That's what's being multiplied by 2 each time. But it doesn't have the a written there, even though our a is 1. And it's because if I multiply 1 times anything, it's going to give me that same number. So the a is implied. Just like with y equals mx plus b, we could have an equation y equals 5x with no plus b, but we know there really is a y-intercept of 0. So it's a concept like that. It's implied with as a 1. All right, where does it cross the x-axis? Never. Never. It approaches. Awesome. So never. It doesn't. It's only going to approach it. It approaches, making this asymptote. The x-axis is that. What's the domain going to be?
All real numbers.
All real numbers. Absolutely, just like the warm-up. So there's a couple ways to write all real numbers. One way is to actually write that out. All real numbers. Another way to write that is x is in between a negative infinity and a positive infinity, which is negative infinity is less than x, which is less than positive infinity. Make sure that you don't include or equal to, because you can't equal infinity, you'll never get there. Or another way, a fancy way of writing this, like you will later on in your high school education, x is an element of all real numbers. Means the same. And what's our range going to be?
All numbers greater than 0.
All numbers greater than 0. So y equals greater than 0. Another way of writing that I don't prefer, you could say 0 is less than y, which is less than positive infinity, because y is in between those things. But it makes more sense just to say y is greater than 0. Right? As the independent variable increases, the dependent variable also increases because it's a positive relationship. It's growth. All right, this next problem, we have two values in our equation. A, that's going to be our y-intercept, and the B is the constant factor, that rate that's changing. So we could plug this into our calculator by plugging in the values as an exponent and pushing enter, or we could know that since our A is our beginning value, that's when x is 0. And then it's going to multiply by 1/2 each time. So this is 4. It's going to multiply by 1/2 to get the next value. So if I were to multiply 4 times 1/2 to the power of 1, when x is 1, it's going to be half of 4. So it'll be 2. Yeah. If my exponent was 2, I could follow the pattern, half of 2 to get 1. If my exponent was 3, I would follow that pattern, half of 1 to get 1/2. Or again, I could plug that into my calculator to see I could plug in any value for x. If I were to go backwards, instead of times 1/2, I can multiply by 2. So if it had an exponent of a -1, it would be 8. All right, so let's graph those points. -1, 8, 0, 4, 1, 2, 2, 1, 3, 1. It looks like it's leveling out, it's approaching 0. But it's never going to be at like a 0 slope. It's always going to keep changing. All right. The shape of this graph is a growth or decay? Decay. Exponential decay. It's an exponential curve. It's a decay. And we know it's a decay for a few reasons. One, it's decreasing from left to right. The values in the table. As x increases, y decreases. But also it's mainly because of this b value. That factor is less than 1. It's between 0 and 1. All right, where does it cross the y-axis? 4. So at 0, 4, that's our y-intercept. And we can see that in the table. We can see that in the equation right there and on the graph. Where does it cross the x-axis? Never. It doesn't. It just approaches it. What's our domain? All real numbers. Write it how you want. And what's our range going to be?
Y is greater than 0.
Y is greater than 0. All right, this will always be the case for all the exponential equations we're using this year. However, sometimes the asymptote might be different if there's more to the equation. Like if it said +5, and that would be a vertical shift, shifting the whole graph up 5 places, including the y-intercept. So watch out for that. It's not always going to be this case, but most likely this year. As the independent variable increases, the dependent variable decreases because it's a negative relationship. Okay, it's a negative. Okay, I don't know if I'm saying this right, but technetium-99M is a drug taken by a patient and then used to study tumors in the brain, lungs, and other parts of the body. The patient takes a 1,000 milligram pill, and the data below shows how much active ingredient remains in the body over a 6-hour time interval. All right, it makes sense when you take the drug, it's in your body and it's active, and as time passes by, it starts to leave your body. So our initial value is what? 1,000. That's our A, because that's our y-intercept when x equals 0. The growth or decay factor is our B, how it changes from value to value. So from 1,000 to 500 to 250, what's the factor? 1/2 times a half. All right. So to write a rule for the function, a rule, it's basically saying what's our equation going to be. Y equals f of x equals, doesn't matter. And we do a times b to the power of x. So it'll be 1,000 times 1/2 to the power of x. And that's our equation. Unfortunately, that formula is not on our short chart, so you do have to memorize it. Next one, in television shows and movies, you often see scientists studying patterns of data, growth of zombies, bacteria, etc. And below is a table that shows the number of zombies over a 4-day period. All right, what's our initial value? 2. And then what's that growth or decay factor? 4. 4 times 4. That's our b. So what would our equation look like? Y equals 2
4
4.
to the power.
Yeah, 2 times 4 to the power of x. Perfect. D says, when will there be over 100,000 zombies? All right, what does zombies represent, x or y? Y. So it's like saying 100,000 zombies equals 2 times 4 to the power of what number? We're not going to learn how to solve it algebraically this year. You're going to learn that later in high school, how to solve for x, when x is an unknown variable. X. But I'm going to show you how to do this in a calculator by finding your table. I'm going to pause here and explain just a little bit. All right, to determine how to solve for this on a calculator, you can use a graph document or Scratchpad. Our equation is 2 times 4, caret key to choose the exponent to the power of x. If you click enter, it will graph it for you. And to access the table, you could either go to menu 7 for table, or the short key, you could just do Control T to get to your table. Control T gets table and back. So we need to scroll down to see where y is greater than 100,000. So y is first greater than 100,000 when x is 8. And then it just keeps growing exponentially. Great. So let's write down those steps real quick so that you know how to do that. We graphed this. And then the shortcut is Control T for table. And then we look for y, where y is first greater than 100,000. And it was after 8 days. Right. Next one. If you invest $25,000 in an account like it's 12% annual interest quarterly, how much would you have in 3 years? So whenever there's percent involved, remember we're going to compare it to that 1. If it's growth, we're adding to 1. If it's decay, we're subtracting from 1. So instead of a times b to the power of x, it's going to be 1 plus r to the power of x here. Well, 1 plus r is rb. So y equals, our starting initial amount was $25,000. And 12%, 0.12. We're going to add that to 1, so 1.12. All right, but it's not changing per year. It's changing how often? Quarterly. And quarterly, how many quarters are there in a year? 4. There's 4 quarters in a year. So for 3 years, so it's every 3 months, yeah. So if there's 4 quarters a year, for 3 years, how many quarters will be? 12. So that's going to be our exponent. So that's something to watch out for. Put that in our calculator. Right, when you enter that in your calculator, you'll get 97,399.4. All right, number 6, moving on along. If you invested a penny on January 1st at 5% interest daily, how much would you have in 1 year? All right, what's our initial value? 0.01 for the penny. All right, and earning 5% interest daily. So 5%, 0.05, we're adding that to 100%, 1.05. Now, it's changing daily. It's increasing 5% daily. How many days are in a year? 365. Unless it was a leap year. So 365. That's that number. All right, so when we put this in our calculator, that little penny becomes $542,118. Because remember, exponential functions, they just increase rapidly and faster and faster. All right, the last one on this page, it says a type of bacteria has a very high exponential growth rate at 80% every hour. If there are 10 bacteria, determine how many there will be in 5 hours, in a day, in a week. So let's start with 5 hours. So for 5 hours, that's going to be our exponent. What's our A initial value? 10. And when are we going to multiply the 10 by? 1.8, because we have to add that 80% to 1. All right, and my exponent's going to be 5 because it's per hour. All right, put that in your calculator. Let me know what you get. 189 188.957-ish, and it's, yeah, so about 189. All right, what about broad day? 10 times 1.8. What would our exponent be for a day? 24, because there's 24 hours in a day. So remember, there's a shortcut on your calculator, copy and paste feature, where if you push the up arrow, scroll up so that it's highlighted, the problem's highlighted, you could just push enter and it copies it. And you could just change the exponent. This one's going to be a really large number. 133. Some of your calculators might have E on this one, but it's about 13,382,588. I know. Wow. It's a big one. So, what about a week? Oh. Alright, so for a week, to determine our exponent here, we multiply by 7 the hours from a day to get 168 hours in a week. If you calculate this, it's going to be a huge number. Your calculator is going to say 7.68742 E43. That's a calculator's way of writing the scientific notation. So what this means, just to get a general idea of how big that number truly is, if you look at this number for days, it has 8 digits. This is taking this number, which already has 1 digit in front of the decimal, and it's going to have 43 more digits in front of the decimal. It's going to be a 44-digit number. Hard to even comprehend. All right, for number 8, we're going to compare the following graphs. It's graphs that shows the population of growth for 2 species. So for the 2 species, we're going to find the growth factor. The growth factor is the B in our equation. That's our B. So we can find that number by looking at what it's multiplying by to get from value to value. So in species X, it goes from 5 to 15, and then from 15 to 45. So what's that multiplying by? By 3. So our B is 3. In species Y, our starting value is 25, and then 50, and then 100. What's that multiplying by? 2. Yep, it's doubling. Multiplying by 2, so it has a factor of 2. All right, so which species is growing faster? X. It's got a larger factor. Larger factor, so it's going to grow faster. All right, let's talk about the y-intercepts. The y-intercepts, that's our A value. So what's the y-intercept for X? Right here, that's 5. 115 will be after that first year. That would be like if it was a geometric sequence at first year. So 5, A is 5, or we can write 0, 5. And then for species Y, it's going to be about 25. All right, so let's write equations for species X and Y. So for X, what number would go first in our equation? The 5, because that's our A, times what's our B? 3, the power of X. And then for species Y,
25.
it's going to be 25 times 2 power of X. Right. For E, it wants to know for which species is 5, 12, 15 a solution. So a couple of options is we could just plug in 5 for our X and see which one's going to give us 12, 15. Another option is we could continue the pattern of the graph. If you were to look at the fourth value here, 405, we would have to multiply that by 3 to get the fifth value. Or for species Y, the fourth value was 400, and this one's going by 2. So that one would have a fifth value of 800. So which one has a fifth value of 12, 15? X. Fill in the following table with the percentage change that created a growth or decay. So for percentage change, we're comparing that to 100%. So we're really comparing it to the value of 1. See how far away it is from 1, and then changing that to a percent. Remember, if it's more than 1, it's growth. And if it's less than 1, it's decay. All right. So the first one, 1.2. How far away is 1.2 from 1? 0.2 away. So as a percent, 0.2 is 20%. And since the original number was greater than 1, it is growth. So I'm going to just say, put an up arrow for growth. 0.75, how far away is 0.75 from 1? 25. So that's going to be 25%. And it's a decay. What about 0.975? 0.025? As a percent, 2.5%. And a decay. Next, the difference from 1, 0.037. So as a percent, 3.7%, and it's a growth. 0.2 is 0.8 away. So what percent is that? 80%. Growth or decay? Decay, let's see. All right, and then 1.003, 0.003 away. As a percent, 0.3%. And it's a growth that's more than 1. Well, that's the 2.8. It's 1.8 away from 1. What would that be as a percentage? 180%. 180% increase. Awesome. The rest of this, the key you can find on Canvas, work out on your own. Don't forget to like and subscribe to my channel.